All right, here we are in College Algebra 1.2, where we're talking about linear equations and rational equations. And we're going to go through and look at some definitions and some examples, and you're welcome to pause and be taking notes as we're going through here. These notes were adapted from Blitzer's College Algebra 5th edition, by the way. And the definition of a linear equation, we don't think about it very frequently, but it's of the form ax plus b. This looks somewhat similar to the equation that you're very familiar with, which is y equals mx plus b. So the a here will become an m down the road, which is going to represent slope. The set of all the solutions to an equation like this is called the solution set. In these equations, we're only going to have one solution. But in future equations like quadratics, sometimes there's one solution, no solution, two solutions. Sometimes the two solutions are the same as each other, which is why I said one solution previously. And some of the things that we're going to do to equations of this type is things like distributing, which you're seeing here, where the 3 is being distributed over to the x and the negative 6. We might have to perform an operation to both sides of the equation, like subtracting 3x, or dividing both sides of the equation by 2, or this property, which is, I haven't thought of this in a long time. Maybe this is the reflexive property. I'd have to look that up. But if a equals b, then b equals a. So if negative 9 equals x, then you can sort of switch the two around and write x equals negative 9, which is a more typical way of presenting a solution. If you're the kind of person who likes steps, then you can use this list of steps. I know people who get very anxious when they hear there are 4 steps needed to solve an equation of this type. They kind of freeze up. So if you're not the person who likes seeing a list of steps like this, let them go. My guess is the majority of you who are watching this video know how to solve this problem, so I'm going to move through it fairly briskly, and if you need to pause or watch any of it again, you're welcome to. Something that's a little bit unusual about this equation, maybe, is that the first thing I'm going to do is distribute, and I like to put a little note off to the side here that says dist for distribute. This tells me what I'm doing on this line or to this equation in order to get down to what I'm going to write next. And the thing that I'm going to distribute is this minus sign. I'm subtracting 7x and I'm subtracting a positive 5. So there's the 2, there's subtracting the 7x, and there's subtracting the 5. On the right-hand side, I'm not going to do anything, just rewriting it as it is. Now, on the left-hand side, I'm going to combine like terms. So I put this little note here that says CLT, and the like terms that I'm looking at are the 2 and the minus 5. And when I do that subtraction, 2 minus 5, I get negative 3. The negative 7x is still there. I could have written it before the negative 3 instead of after. I chose to write it after. And on the right-hand side of the equation, we still have the 13 minus 3x. The next thing that I like to do, which is different than what a lot of my students like to do, is I like to then move the variable first. I like to get all of my x values, in this case, onto one side of the equation. And I think if you look at this for a couple of seconds, your instinct will be what mine is, which is to add 7x to both sides. I like to do this to both sides, adding 7x, so that this will turn into a 0, and the negative 3x's plus the 7x's is going to result in a positive number of x's, which I like. So the negative 3 will still be there on the left-hand side. The negative 3 will still be there on the left-hand side. The 13 is still there on the right-hand side, but negative 3x plus 7x is equal to positive 4x. Now, if you're the person who likes to come in and put plus 7x and plus 7x, you can do that. I don't do that anymore because vertically on my paper it takes up more space, which pushes my work off the screen faster, and I'm trying to keep as much content on the screen as I can. It applies the same as if I'm using an overhead projector in an actual classroom. So that's why I put these notes off to the side like this. Now that I've moved all of my x's over to the right-hand side of the equation, I'm going to get my constant values. Constant is the opposite of variable or changing. So let's get the constant values over to the left-hand side. We'll make that happen by subtracting 13 from both sides, which leaves me with negative 16 on the left. Sorry, my pen is acting up as usual. Negative 16 on the left. Those positive 4x's are still there on the right-hand side. And then in order to finally isolate the x value, I'll divide both sides by 4. Negative 16 divided by 4 is negative 4. And on the right-hand side, the 4's cancel, leaving me with a conditional equation, as it turns out. The truth of the original equation is conditioned upon x equaling negative 4. So one solution to this equation. And then we have the pleasure of looking at linear equations that involve fractions. And let's go right down and look at this one. If we were meeting in person, I would ask you this question, but I'm going to ask you anyway. What do you like least about this equation? And my hope is that your answer is fractions, or there are denominators, which is what really makes a fraction a fraction. I hate denominators and fractions. So the first thing I want to do is make those denominators go away. And the only way that I can think of making a denominator go away is if, for example, there was a 3 up here, I'd be able to cancel out the 3's. Thing is, if I put a 3 up there, I'd have to put in a multiple of 3 here and a multiple of 3 here. This would reduce the 6 a little bit. I'd still have a 2 down here, and the 3 doesn't do squat for the 4, so maybe 3 is not the best choice. I want to choose a number large enough that it's going to allow me to reduce all of my denominators to the point where they're gone. So 3 is obviously not large enough. 6 is getting a little bit closer. If I put a 6 here, and if my pen works, a 6 would reduce with the 3, it would turn into a 2. A multiple of 6 here would knock out the 6 in the denominator, and a 6 multiplied into this numerator would partially reduce the 4. It would turn this into a 2 and this into a 3, but I still have this additional multiple of 2 in the denominator. What that tells me and my trained eye is that 6 wasn't large enough, but 12 would do it. Putting that additional multiple of 2 into the 6, right? 6 times 2 is 12, will allow me to get rid of this 4 entirely all in one go. Let me erase these things and let's write it up with a 12. Incidentally, 12 is the least common denominator. If we were going to make common denominators for all these fractions, 12 would be the common denominator. Why am I not doing that? Why am I not actually creating a common denominator? If we didn't have the left-hand side of this equation, or the equal sign, if we just had the two terms on the right-hand side, then it wouldn't be called an equation anymore. It would be called an expression. And we could do this addition problem, but only if we had a common denominator. So we would have to achieve a common denominator. In this case, the common denominator would be 6, actually, because we don't have that multiple of 4 anymore. But if you take this equal sign, you turn it into a plus sign, try to add all three of those together, your common denominator would be 12. So what is it? And if you want to think of it that way, if your mind is already kind of trained to be able to see what the common denominator would be, great. Think of this as multiplying the entire equation by the lowest common denominator, not divisor, the lowest common denominator, over 1. And we just talked about how the LCD would be 12. So I'm going to take 12 and multiply it into this numerator of x plus 1. And this multiple of 1 is going to be coming down or multiplying into these denominators, and it's not going to affect them. So I still have a denominator of 4 here equals multiplying the 12 into this numerator, so 12 times 1, original denominator of 6, plus multiplying the 12 into this last numerator of 2 minus x, all over the original denominator of 3. I haven't actually done any multiplication yet. I've just sort of placed the multiples of 12 into all of my numerators. The next thing I'll do is I'll start reducing each one of those fractions one at a time to get rid of my denominators. When I cancel stuff out, and especially if it doesn't cancel out entirely, like this is just, we're just reducing here. 12 divided by 4 makes 3. So maybe I put a little 3 up here. Maybe immediately I come down and rewrite it. There's a 3 still there, and the x plus 1 is still there. The equal sign is coming straight down. Notice I try to keep my equal signs lined up so that I can see how the story is playing out in my notes when I'm doing a review. Okay, let's go to the next term. The 12 is reducing with the 6. 12 divided by 6 is 2. So I've got 2 times 1. If you want to put the times 1, you can, or let it go. And then I might even leave this space right here so that I can put my plus sign, so that it's all lining up. The 12 divided by 3, that reduces to a 4, a little 4 there, and 4 times the 2 minus x. Great news, we now have an equation that doesn't have any fractions in it. No more denominators. This equation I think I can work with. So what are we going to do next? And if you want to put a little note here that says that we simplified or reduced or something like that, you're welcome to do that. The next thing I'm going to do is distribute. How do I know to distribute next? Well, I'm not the best math student. I'm looking at the equation and I'm thinking, well, what do I know how to do based on this current scenario that I'm looking at? Well, the only thing I really know I know how to combine like terms. I know how to, what I do to one side of the equation, I do to the other. I know how to distribute. Ooh, I can distribute. Let's just do that and see what happens. And sometimes that's how you have to start. So I'm going to be distributing here, and I'm going to distribute over here. So let's do both of those. We get 3x plus 3 equals 2 plus 4 times 2 is 8. 4 times negative x is negative 4x. All right, we don't have any more grouping symbols now, so now we can combine like terms. Is it worth writing that down? Sure. CLT for combined like terms. It's only the 2 and the 8 that are going to be able to add together. So my 3x plus 3 is there. I've got a 10 and a minus 4x. What am I going to do next? Group all of my variables to one side of the equation. Let's get all the x's over to the left-hand side so that we have positive 7x's. Add 4x. So again, that's a little note about what I'm doing to both sides of my equation. 3 and 4 make 7x's. The positive 3 is still there. The 10 is still on the right-hand side. The negative 4x and the positive 4x, those canceled out. That's why we did that, to eliminate the x's from the right-hand side. Now we can get our constant values together on the other side of the equation. So let's subtract 3 from both sides. We get 7x equals 7. And to finally isolate that x value, to get it really all alone there on the left-hand side, I'm going to divide both sides of my equation by 7, giving me a final answer, at least I think it's my final answer, of x equals 1. I'm saying maybe it's my final answer because I remember that my original equation had fractions in it. And when your original equation has fractions, when it's a rational equation, it's worth glancing up just for one moment. And the thing that I'm looking at, or looking for in my original equation is my variable, does it appear in the denominator at all. In this case, it doesn't. So I don't really have anything to worry about. But we will get to the point where we're working with equations that have the variable in the denominator. And in this case, if one of our denominators said x minus 1, I know I'm kind of writing over the top of what's there already, but if that denominator said x minus 1, would that be a problem? It would, because the solution that we got was x equals 1. And if I take that value of 1 and I bring it up and I plug it in, which I should be able to do with a solution to an equation, this turns into 1 minus 1, which is 0. So what? So it's a 0. A 0 in the denominator does not fly. That's division by 0. That's undefined. So when we get to the point where we're working on equations that have the variable in the denominator, we're always going to have to do that extra step of doing a quick check to make sure that our proposed solution does not accidentally cause division by 0, or maybe eventually we'll have to worry about the square rooting of a negative number. We might have to worry about the domain of a logarithm or a natural log, something like that. So as we get further into the course, I'll remind you that we need to keep an eye out for that. But since this does turn out to be a good solution, doesn't cause division by 0, I'm going to put a box around it. The definition of a rational equation, an equation containing one or more rational expressions, okay? These equations will have variables in the denominator. So there it is right away. We were just talking about this. They've even italicized it in these notes. And there it is. What some teachers will do is they'll tell you that the very first thing that you should do is write down a note about what x values you must avoid. And in this case, what's the one x value that I have to avoid? It's an x value of 2, because 2 minus 2 in the denominator would cause division by 0, and we said that's not going to fly. All right, so let's try to solve this equation then. And if you like this idea of immediately putting yourself a little note, x is not allowed to equal 2, and maybe put yourself a little cloud around it or something, or a sad face, or whatever you want to do. I think it's a good way to go, putting this note down immediately. If you can train yourself to have that habit, I think it's a great idea. You could even write it down toward the bottom of the page as a reminder down here that x is not allowed to equal positive 2. That way, once I get down there, at the end of my solution process, I'll see it again. Okay, so let's try it. You're looking at this equation. What do you dislike most about it? There's fractions, there's denominators, there are denominators. How do I get rid of the denominator? Same way, you have to multiply by the right quantity into the numerator so that it will cancel out or reduce with the stuff that's in the denominator. In this case, what we're going to multiply by is the denominator, the LCD, the least common or lowest common denominator. I'm going to take the 2 from my first numerator and I'm going to multiply it by, if my pen will work, I'm going to multiply it by x minus 2. And I'm going to keep the original denominator of x minus 2 equals the original x in my next numerator. And I'm going to multiply it by x minus 2 all over its original denominator of x minus 2 minus, and there's a 2, that's this one. There's a lot of 2's in this problem, so we've got to be careful. I'm going to take that 2, and I'm thinking of it as a 2 over 1, and I'm multiplying into that numerator this same multiple of x minus 2. I should have said this earlier. If you have multiple colored pens or pencils or something like that, or even if you want to go back with a highlighter, what we did to our original equation. See, now I want to erase this. It's in my way. We took this entire original equation and we multiplied it by the LCD over 1. And in this case, the lowest common or least common denominator was x minus 2. So I'm multiplying all of the terms in my equation by x minus 2 over 1. And here's where, if you had a highlighter, you could come in and maybe highlight this numerator here, and then you could highlight this, or highlight this, and highlight this, just so you can see where those are coming from. Or you could have written them in a different colored pen, or colored pencil, whatever. Whoa. How did that happen? Sorry about that. Alright, so I've multiplied this x minus 2 into all of my numerators. Now we can start reducing. So these are going to cancel, and these are going to cancel. And that's it. This 1 that's in the last denominator, we're going to be able to disregard that. So let's clean it up and see what we have left. There's a 2 on the left-hand side of the equation. Bring the equal sign straight down. There's an x remaining from that first term. And then there's this minus sign. And then there's the 2 and the x minus 2. Notice also that when I multiplied this x minus 2 into all of my numerators, that I put it in parentheses. And it might have seemed right when I was doing it, or you're just trusting that I know what I'm talking about. But now you can see just the actual utility of it, because the next thing I'm going to do is distribute. I have to distribute multiplication by this negative 2 into these two terms in the parentheses. The 2 is still on the left-hand side of the equation. The x is still on the right-hand side. Negative 2 times x makes negative 2x, and negative 2 times negative 2 makes positive 4. So be careful and remember that when you distribute, you do have to take that minus sign with you. As we've done before, we need to get all of our variables onto one side of the equation. That's what I like to do next. As it turns out, they're already on the right-hand side of the equation, so all I have to do is combine like terms. That gives me 2 equals negative x plus 4. You could add the x to the left-hand side and subtract the 2 over to the right-hand side. I'm just going to do a minus 4 on both sides. Leave the variable where it is. 2 minus 4 makes negative 2 on the left, a negative x on the right. 4 minus 4 is 0, so those are gone. I have to deal with this negative sign in front of the x now. I'm going to make that go away by multiplying both sides of my equation by negative 1. That switches the sign there. It switches the sign there. I've got this proposed x value of 2, and now you're seeing why it was so important that I called it a proposed x value. If we do a check, we see that x is not allowed to equal positive 2 because it causes, that's an S, so bad, causes division by 0. Therefore, no solution. The solution is, oops, I went off the bottom of the screen, sorry about that. So the solution is that there's no solution. Are you happy about that? Probably not. Could it potentially be valuable to somebody that there's no solution? Sure. If my goal is to produce a certain number of items, which is going to allow me to make a certain profit, and I need to make that certain profit because I need to pay my bills or feed my family or something like that. If my next door neighbor is a math professor and I tell him some details about what it is that I'm doing or trying to create, and he does some or she does some calculations and says, hey, based on the price that you want to sell your things for and the number of them that you can create per month and get them to market and the overhead of doing the business, and that you're never going to be able to profit what you need to profit in order to keep a roof over your head and pay your bills and feed your family. There's just no solution. Yeah, I want to know that right away because I don't want to go and do whatever that business is because I'm going to end up homeless and without a family, and all of a sudden that story takes a really bad turn. But you see what I'm saying? No solution can be a very valuable solution. There are some different types of equations. You might have heard about these in a previous algebra course. I just talked about these in my intermediate algebra course. An identity. If you notice this equation right here, if we combine like terms on the right-hand side, you get x plus 3 equals x plus 3. That is a true statement all the time. Pick any x value you want, positive, negative, 0, square roots, I don't care. Plug them in, that statement's going to be true. It's true for all x values. So maybe your solution set to an equation like that turns out to be the interval going from negative to positive infinity. In other words, all real numbers. A conditional equation is the one that we're most used to, where you solve the thing and you get one x value in that case, or if it's a quadratic, maybe you get 2. And finally, there's this inconsistent equation. If we subtract x from both sides of this equation, we get a statement, an equation that says 0 equals 7. I don't care what x value you give me, 0 is never going to equal 7. Okay, so this one has no solution. You might see that represented as the empty set, which is these kind of squiggly brackets that have nothing between them. Or you could see a circle with a slash through it that also represents the empty set, which is sometimes referred to as the null set. N-U-L-L-S-E-T, the null set. So there are some little processes for you solving rational equations. They're not, hopefully you're seeing, they're not as difficult or intimidating as you once thought. If we keep in mind that the first task is to multiply the equation by something large enough or complicated enough that we're able to cancel out or reduce away all of our denominators. And after that, it turns into an equation with no denominators that you know how to solve no problem, hopefully. All right, thanks for joining me for 1.2. Hopefully you'll be seeing me in 1.3. Thanks so much.